Hello there. Welcome to multiple linear regression. Congratulations on finishing simple linear regression model. In simple linear regression model, you understood that the scattered data, the independent variable and dependent variable can be related by an equation wherein dependent variable is equal to y-intercept plus coefficient and independent variable. It's a very simple formula to fit in the data. And if your project or case study you are working on has only one independent variable and you are predicting a dependent variable based on only that one independent variable and the equation looks like linear, then you are in luck. You can do simple linear regression and get your analysis done, get your prediction done. But usually you might end up in projects like this. I am taking an example of house price here. So house price depends on various features. One of the feature might be family income. What is the family income of people living in that locality? As the family income increases, the affordability increases. So the housing price might be high in that locality. The average family income is high, so prices might be high, right? That's one relation. Second feature it might be dependent on is amenities. If there are very good amenities available, then yes, the house prices might go up. Likewise, crime rate. If crime rate is high in that locality, then house prices goes down. Now consider this. Now you have one dependent variable and three independent variable to play around. That is called multiple linear regression. How will you predict the y now? You have to have a formula wherein you can fit all these independent variable. Through that formula, you will come up with a straight line which actually takes in account all these independent variable. And the formula might look something like this. Y, the dependent variable, is equal to b0, the y-intercept, and then b1, that is coefficient for variable 1, feature 1 and feature 1 value. Coefficient for feature 2 and feature 2 value. Coefficient for feature 3 and feature 3 value. So that is the multiple linear regression. It's an extension of simple linear regression, but simple linear regression had only one variable to play around, one independent variable. In case of multiple linear regression, you will have more than one independent variable to play around, but it is still a linear model. It is still continuous numbers and it is still a linear regression model. In real world, you might get something like this. You might get a scattered plot of y versus x. There are points, scattered points based on different feature values. So you will get a data with lot of features, and based on that feature you have to predict dependent variable. And then you have to come up with this formula. Through your training data, you will calculate this b0, b1, b2, b3, the coefficients of these features, and then you will derive this formula. Once you have derived the formula based on the training data, then you are good to go. So overall flow is same, but the only difference is instead of one independent variable, one feature value, you have multiple feature values to play around. So you will get multiple coefficients. I hope you got clear distinction between simple and multiple linear regression and how multiple linear regression works. Let's move on and let's do some hands-on, and then you will get the real exposure to this multiple linear regression. I will see you in next lecture. Hello there. Welcome to this lecture. And congratulations, you are making a very good progress. I am very happy for you. Now that you understand simple linear regression, it will be easy for you to correlate things and understand multiple linear regression. After all, it is just few more independent variables, right? Awesome. Good. So let's begin. You already know. Yes, import library. So let's do that very fast. Import numpy as np. I could actually directly paste it, but I do it with you so that you follow this through and you type at the same speed I am typing. I want you to follow each and every step, and I want to be with you. That's why I'm not copying and pasting things here. I'm writing it along with you. Okay, buddy? Let's do it. Import pandas as pd. Import seaborn as sns. And import matplot lib.py plot SPLT. Let's run it to make sure I did not get any typo. Okay, looks good. Next, you are going to import the dataset. In previous lecture, you already understand where is the dataset and how to get it. Once you have that dataset stored on your computer, you can read it in a pandas data frame using read underscore CSV. Let's do that. df equal to pd dot read underscore CSV, and over here put R and put the complete directory structure including the file name over here. The file name is autompg.data, and this file does not have header. So you are going to write a command header equals none. The delimiter is going to be backward slash s and plus. Right? Let us run this. I want to show you something. Let's run df dot head. What do you get? You get the data, but the header, look at this. It says 0, 1, 2, 3, 4, 5, 6. If you want to give the name to these headers, you can give it right here. Just run names command and put your names here. The names are going to be, the first one is miles per gallon, cylinder, next one is displacement, and then horsepower. Next one is weight, WEIGH, acceleration, then mod year, and origin, and then car name. I think we are done. Let's run it again. Very good. Now we got all the names right. Awesome. So this is something new you learned compared to the previous lecture, that in pandas data frame you can put the header as none if you don't have header in your dataset, and then you can provide the names of those headers using the names command. Good. This one was data import. What is next stage we start now? Data exploration. You got it. Data exploration. Awesome. Markdown. First thing we're going to do is find out the shape of this data, and that is easy. Shape. There are 398 records and 9 columns, 8 features and 1 target, so total 9. If you look at this horsepower, oh sorry, I got the spell wrong. Let me correct this, twice there will be confusion. So good, now we got it right. Let's open the data, and when you open the data and you look at that data, you will see some of the horsepower values have question mark. The first thing is to get rid of these values. Let's do that. There are different strategies to get rid of this kind of data, either to delete it or to replace those question marks with the mean value or average value. There are different ways of doing it, but for this lecture and just for understanding, I'm going to remove it and we will play around with the remaining set of data. So let's remove that. We're going to run this command. Our data frame df equal to df dot drop, because we are going to drop a few observations, of course. So df dot horsepower equals question dot index. Close this to here. We press this. Okay, and let's print the df dot head. It didn't lines up. It's saying data frame object has no attribute horsepower. I still got it wrong. Horsepower. Okay, let's run it again. Very good. So we got rid of the observations which has question mark in horsepower. Let's see the shape again. df dot shape. Now it's 392. That means there were 6 rows of data with question mark in horsepower value, and we just got rid of them. Okay, let's move on. If you look at this data, the horsepower, it is very understandable. Horsepower value will be a numeric value, but because some of the values were question mark, the pandas data frame, which when it took the data from the data set here, it might not have considered the horsepower as a numeric value. To find that out, we are going to run this command df.apply map. Over here we're going to say np.is real, okay, and run it. Look at this, it says mpg are true. That means yes, they are, all the values are numerical, it's real numbers. Cylinder, yes, numerical. Displacement, numerical. But horsepower, look at this, false. That means the data frame has not considered horsepower as a numeric value. So what do? We need to convert them to numeric value. Let's do that. df horsepower equals pd dot to underscore numeric df. Once again, our horsepower, the to numeric function in pandas data frame class will convert the horsepower to a numeric column. Okay, let's run this, and let us run the same command again. Let's run it. So this became a true numeric value. Only field remaining which is not a null value is car name. Other than that, all other fields are numeric values. Now let's find out if any of them have null value, right? This is all part of data exploration. You already know this. df dot is null and sum. Control enter. Over here, none of them have null value. Awesome, you are in good luck. We are done with the basic check of data in data exploration. But here comes the fun part. When you have so many variables to play around, all of those variables might not be required in your data model. You have to understand two very important things in case you have so many variables. First, we call them independent variables, and we expect them to be not related to each other. So first thing, we are going to find out if any of these variables are related to each other. That means if one grows, other also grows in value. If such kind of relations exist among the independent variables, then we don't need those variables. We don't need both of those variables in our data model. We need only one of them. So that is what is called multi-collinearity, and that's what we're going to find out, if any of our independent variable has multi-collinearity. Okay, so there exists a very simple method of finding multi-collinearity. There exist various models, various methods of finding multi-collinearity. We are going to check two of them. One I regard as a simple model, and that is called finding out the correlations among these independent variables. So if you just say df.core and run this, this gives you a matrix here, and you can very well see how are these variables related to each other. So if you look at cylinders, it is very closely aligned and dependent on displacement and horsepower and weight. So these three variables, they are very much related to each other. Cylinders, displacement, horsepower and weight. So right here we got a multi-collinearity. There is one more method, and that is called calculating variance inflation factor. Let's do that one. So now at a high level, we know that cylinders, displacement and horsepower and weight, they are very much related to each other, and we got a multi-collinearity on our data. So now we are going to work on variance inflation factor, also called VIF. Variance inflation factor, VIF calculation. So what do we need for calculating variance inflation factor? First and foremost, we need to import the required functions from the required library. Let's do that. So run this command. From statsmodel.stats.outlier influence, import variance inflation factor. This is the function we're going to use, variance inflation factor. So once you import the function, the next thing to consider is we are going to calculate variance inflation factor among independent variables. So the first thing is we don't need dependent variable like MPG. And second, for calculating variance inflation factor, we first have to convert all the independent variables into numeric numbers. It cannot remain alphanumeric. So let's do that first. df1 equals df dot get numeric data, okay, and then our x is going to be df1 dot drop. So what are the attributes we are going to drop? We already discussed about mpg. We're going to drop mpg because it's a dependent variable. In addition to that, I am suggesting we drop origin here because I don't think it's going to contribute much to the model. How will the car name or origin is going to contribute to the model of MPG when we have so many other variables to play around like displacement, horsepower, weight, acceleration and mod here, right? So let's get rid of that right now, and then we're going to say axis equals 1. This is just a very simple command to get rid of any attribute in your data frame. So far so good, but let's run it to make sure we imported correct function and we got this right. Let's do that. We got it right. Now comes the fun part, the variance inflation factor VIF part. First thing we're going to do is create an instance of data frame class bd dot data frame over here, and then VIF factor space here equals, we are going to call that function variance inflation factor and pass the values, x values. We need to pass each x value one at a time, and that's why we will run a for loop kind of thing here. For I in range x dot shape 1. Got it? Good. Next, VIF features equals x dot columns, and let's call VIF dot round 1. Okay, let's run this. Okay, I got something wrong. What is this? VIF features equal x. Oh, again typo. Not a big deal. Okay, now we got it. Look at this. The thumb rule is any value with VIF greater than 10, you should get rid of them. Start with the one which has highest value. Over here, weight has highest value, so I'm going to remove the weight first. Okay, let's run it again. And say weight. Weight is gone. Next we have model year, that is sorry, and cylinders. Cylinders has higher value, so next we are going to remove cylinders. Very good. We are getting near. We are left with few acceleration and mod year. Mod year has higher value, so let's get rid of mod year. Model year. What do we have now? Displacement and horsepower. Let's get rid of horsepower. We are getting closer. See, acceleration is already less than 10, so that is good to go. Okay, let's remove horsepower. So sad, we did so many things for the horsepower. Converted it, got rid of those question marks, converted it to the numeric value, but hey, now we don't need that. Funny, right? Okay, let's do that. Awesome. So finally we have two independent variables, displacement and accelerations, and those are going to be part of our data model. Look at this. This is called data exploration. When you understand your data, your life becomes very easy. We started with 8 independent variables, but now when it comes to creating our model, we know we don't need 6 of them. We only going to need 2 of those independent variables to predict MPG. Good job. Before we conclude data exploration and move on to data preprocessing, let us do one more thing. Let us draw a scatter plot of these two independent variables, displacement and acceleration, and let's see their behavior. Let's do that. And over here we're going to use the Seaborn function called pair plot. Pair plot. This is first time you are using it, and I'm sure you're going to love it. Pair plot df1 and x values are going to be displacement and acceleration, and y values is going to be our MPG. Let's say size is 0.7 and say plt.show. Did you get it? Oh, let us increase the size. It looks very small. Okay, now we got it right. Yeah, they look like a linear regression. Well, yes, they look like a good fit for multiple linear regression. Like this looks a linear behavior. This also looks kind of linear behavior. I can draw a line here and predict. But looks like a huge standard deviations. And for here, polynomial regression might be a better fit. But hey, we are in a lecture of multiple linear regression, and I think multiple linear regression fits well for both of them. Our feature selection step has not finished. So far what we did is we got rid of multi-collinearity. That means we got rid of the independent variables which were very much related to each other. We still have two variables and we still have to decide which of those variables have the greatest impact in your real world project. You might start with, for example, 15-20 attributes and you are left with, let's say, 7-8 attributes or maybe 5-6 attributes after getting rid of multi-collinearity. Now you have to run those remaining attributes in one more round of selection process, and there are various selection process available in multiple linear regression modules which will help you to find out which among the remaining independent variables should be considered for your final data model. One of those criteria is called backward elimination, and that is one we are going to use for this model. There are various, there are forward selections, there are backward elimination, there are bidirectional eliminations, and I'm going to explain each one of them. Okay, to use backward elimination, we first have to import the required functions from the required libraries, and we're going to import stats models.api as sm. So at this point, if you look at this, we got a formula which is y equals b0 plus, let's comment this, b0 plus b1 x1 plus b2 x2, wherein y is actually our MPG, equals b0 going to be a constant and then b1 coefficients, and this one is going to be displacement, and once again b2 another coefficients, and over here, and this one here is going to be acceleration. To make backward elimination work, we have to put an independent variable here also. It cannot be just b0. So the way it works, we first have to say MPG equals b0 into 1 and then these values here. So that becomes our formula. So that means we have to have one more feature added to this table, and that feature has value only 1. So to add that, there is a very simple command. We're going to say x equals sm dot add constant, and that's it. It is going to add a constant line with value 1 for x. Let's print x and then you will understand. Over here, so it has added one more feature called constant, and it has put these values 1 1 1 1. Constant, displacement, acceleration, right? Good to go. Next, over here we are going to continue in this only. Let's comment this guy, regressor OLS. That's the name we are going to create. We can put any name here, and our sms.ols y and x, we're going to fit it, and now we're going to print the summary. Okay, and let's run this. Very good. So what are we looking for in this? We are looking for this value p greater than -t, and any feature value greater than 0.05 is significance level is 0.05. So there is a big theory about what is p, and I'm going to write a blog on that, and I will put it as one of the lecture. If you want to understand what is p, what is null hypothesis, and how does p work, you can go through that. But for now, understand the thing we are looking here is for any of the feature value, this one here, p greater than t, should not be more than 0.05. If it is more than 0.05, which is the case here for acceleration, you should get rid of that feature. And over here, look at the warning. Condition number is large, 1 point, this condition number here. This might indicate that there are strong multicollinearity or other numerical problems. That means even after all those exercise here, we could not get rid of one of the collinearity, which is very strong relationship between displacement and acceleration, as we saw in correlation here. Displacement and acceleration, they were very related, 0.95. It's a very high number, but we could not get rid of that when we calculated IVF. But over here, when we do this summary, it is still indicating that you should get rid of acceleration for your final model. So let's do that. Let's get rid of acceleration and let's run this guy again. Let's say x equal to x dot drop Okay, let's run this again. Of course, our r square will go down. The reason r square goes down, you add more variables, r square will go up. If you reduce number of variables, r square goes down. So that's why we say in data science world that when it comes to understanding whether your data model is working or not, it's not only r square, there are various other things. Even r square of 0.068 might be a good model because it depends on lot other factors too. Okay, let's move on. So there is no p greater than 0.05 as well as condition gone down, so that warning has disappeared. So looks like we got a good model now. We have to play around with only one variable, displacement. Look at this. We started with 8 independent variables, but when it comes to creating our model and passing to that model the variable which has a strong effect on our target variable, we are left with only one, and that is displacement. That is the wonder of data exploration. You are on the right path, my dear friend. Let's move on. We already did part of data pre-processing because we got our x and y ready. Now we have to create our training set and test data set, which is very much similar to what you have done in simple linear regression. From sklearn.model selection, import train test split x train x test y train y test equals train test split x y test size equals 0.2 and random state is going to be 0. Let's print that. X train dot shape x test dot shape y train dot shape y test dot shape y test. Yes, here we got it right. 313 for train x train and 79 for x test. So far so good. Now let's train our model. From sklearn dot linear model import linear regression and linear underscore reg equal to linear regression. Yes, and then very good. Next we are going to train the model, and it is similar to what we have done in simple linear regression. Awesome, our model is trained, and now we are going to predict y. And next we are going to predict y based on x test, and that's the command here. Very good. X y predict is there, and now let's compare the values. Let's understand how close we are in our prediction. Compare the values of y pred and y test like we did in the linear model, right? Let's do that. Okay, run this command over here. 28, 29, 22, 26, 12, 13, 30, 29. I think it looks pretty good. In few places it is far off, like 38, 28, but few places it is very close, 28, 29 and 12, 13, 33, 29, not bad. 19, 21, not bad. Yeah, looks pretty good to me. Let's print a distribution plot of the y test value and y prediction value, and that will give us a fairly good idea of how well we were able to predict the y values. By now I hope you already know how to plot distribution plot. I know you do. So let's do that. Let's say sns.dist plot and plot our y test. We're going to say color equals, let's say red, and label equals actual values, and let's say we don't want histogram, so hist equals false. And let's do the same thing for y pred, but this time we're going to, for y pred we're going to give color as green, and we're going to put the label as predicted values, and then here it will be pred, and let's show it. plt.show. Good, let's see. Wow, here I think we got it pretty close, right? Look at this. Up until MPG 10 we are very close to each other, but and then after that there are some variance increased, and after that we are again close. So this is a reasonably good model we have worked on. We have developed a reasonably good model on a real world data. Don't forget, this is a real case study done by the university, and we are able to predict very close. And this model is pretty good model you have worked on. You should be proud of yourself. I will see you in next lecture.